This lecture covers special types of cash flow streams, loan amortization, and how to find the value of anything. I'm your professor, Dr. Stephen Haggard. In our last lecture, we looked only at working with lump sums. In other words, investing a large amount of money to receive an even larger amount of money down the road in a single payment. Most of the time in the real world, we don't see investments working like that. People will invest small amounts over their working careers to build up a nest egg. Conversely, they may invest in that nest egg to receive a series of payments from an insurance company or other retirement funding provider. And so we see that in the real world, we have to look at different types of cash flow streams. The first part of this lecture describes the different types of streams that you might receive or pay and provides a formula or method to value each. The first special type of cash flow we'll discuss is called the perpetuity. A perpetuity is a cash flow stream that provides identical cash flows in each period extending to the end of time. In other words, it goes on forever. Now, you say, maybe there is no such thing as a perpetuity in the real world. Actually, there are. The British and the Canadian governments have sold bonds called consols, and all you do is make a lump sum investment up front, and then you receive a perpetual cash flow stream which you can leave to your heirs. People bought these hundreds of years ago, and there are still their heirs collecting these payments today. Also, we see that preferred stock works this way because preferred stock pays a fixed dividend every quarter or every year, and there's no maturity date on preferred stock, so in theory it goes on forever. Now you might think it would be difficult to value such a stream of cash flows, but in actuality it's quite easy. All we do is take the amount of each identical cash flow and divide by the required rate of return as a decimal, not as a percentage, but as a decimal. And that gives us the present value. We can also fool our calculator into calculating the present value of a perpetuity by entering in 10 nines as the number of payments. This allows us to fool the calculator into thinking it is dealing with infinity because the present value of any payments beyond that is so small that it does not affect the present value of that stream of cash flows. Here's an example of how to fool your calculator into working a perpetuity for you. Our perpetuity pays $100 per year. Your required rate of return is 10%. Now notice I didn't say per year, but unless you are told otherwise, you assume that. What is this stream worth to you? Well, our formula would tell us that we would take 100 and divide by 0.10. So the present value of that perpetuity is $1,000. Now I actually find the formula easier to use, but if you can't remember the formula, then perhaps you can remember how to use your TI-BAII 2+. And here we go. First thing we want to do always with our calculator is second, clear TVM, and that clears its mind of what it formerly has worked with. Okay, 100 payment, that's the amount of the recurring cash flow. 10 I per Y, and then we're going to put in as many nines as it will take and hit N. That's basically trying to fool the calculator into thinking it's dealing with infinity. And at this point we can compute the present value. Notice that we get $1,000, which is exactly the same as the formula. However, notice that there is a negative sign. Once again, this is due to the sign convention of the TI-BAII 2+. The next special type of cash flow we'll discuss is the growing perpetuity. Like a regular perpetuity, it's a stream of cash flows that goes on forever. But unlike a regular perpetuity, the growing perpetuity grows at a constant rate. Do we have any examples of this in the real world? Well, common stock dividends may come close. If a firm's stock dividends grow at a regular rate, then we can loosely model those dividends as a growing perpetuity and use that to find the value of the stock. Fortunately, we have a formula. The present value of a growing perpetuity is equal to the first cash flow in that series divided by the difference between the required rate of return on the investment and the growth rate of the cash flows. Now notice that R must always be bigger than G. If R was less than G, then the present value would wind up being negative. Let's work an example with a growing perpetuity. An investment company offers you a stream of cash flows that grow at 5% per year. The first payment of $1,000 is due 1 year from today. You require a return of 10% on this investment. How much is this investment worth to you today? Well, the formula is present value equal to C sub 1, that's that very first cash flow at the end of period 1, divided by the difference between the required return on the cash flow and that growth rate. So C sub 1 is equal to 1,000, and we change our required return and growth rate into decimals from percentages. So we have 0.10 minus 0.05. And when we do the math, we get $20,000. That means that today you would be willing to pay $20,000 for a series of payments that starts a year from now at $1,000 and grows at 5% per year if your required rate of return is 10%. With a few minor adjustments, you can fool your calculator into doing growing perpetuity calculations. First of all, we will put C1 into PMT. That's the cash flow at time 1. And we're going to put I per Y as R minus G. And if you look at the formula, you can see why that is. And finally, to get to infinity, or close enough, we're going to put a bunch of 9s in for N. So we're going to use our example here that we've already calculated using the formula. And we'll use our TI-BAII 2 plus calculator. First thing we want to do is to clear the time value of money. 1,000 payment, that's cash flow at time 1. 5 I per Y because we had 10 minus 5. And then a bunch of 9s, many as it'll take for N, and compute the present value. Notice that we get $20,000 present value, which is exactly the same result that we obtained using the formula. So if you can't remember the formula, but you can remember these little adjustments that we did here, then you can do a growing perpetuity on your calculator. Now we're going to move on to a type of cash flow that's much more familiar to us. An annuity is a set of identical cash flows that goes on for a finite amount of time. Finite means there is an end to it. This is different than a perpetuity. We're going to discuss two types of annuities. Ordinary annuities. The cash flows occur at the end of the period. In finance, we always assume, unless told otherwise, that the cash flow occurs at the end of the period. That means that you receive the first cash flow 1 period from now, or time 0. Annuities are a little different. You get cash flows at the beginning of the period. So when you read problem statements, you need to figure out whether you're dealing with ordinary annuities or annuities due. When in doubt, assume you're working with an ordinary annuity. Annuities due problems will say things like, the first payment is due today, or the first deposit to your account is made today. What do we see in the real world as examples of annuities? Well, most of you are probably familiar with car loans. You borrow money to buy a car, and then you make monthly payments. Do those payments go on forever? No, in most cases, car loans are 3 through 7 years. A lot of them are around 5 years. So you're going to have 60 payments, and then the car is yours. Mortgages to purchase houses are very similar, only instead of making 60 payments, you make 360 payments over a 30-year period. And finally, retirement can be thought of as annuities. If you invest your nest egg for a series of identical payments that only last a certain amount of time, then that is an annuity, but the payments are flowing to you instead of from you. Now the formula for annuities is complex. If you are really interested in the formula, please see your text or Google it. But the formula is actually too complex for most students to execute correctly. So I teach the method of using the TI-BAII 2+ calculator to handle annuities. Now we're going to start with ordinary annuities, the most common type. Here's a typical ordinary annuity problem. In this one, we will be finding the payment. You borrow $60,000 for 5 years to purchase a BMW. The interest rate is 6%. How much are your monthly payments? To get to our solution, we need to know a few things about the way such loans are quoted. When we borrow money, the amount that we borrow is the present value. So that $60,000, that's going to be the present value. Unless you're told otherwise, we assume that the interest rate is an APR, or annual percentage rate. Thus, a 5-year loan at 6% per year is actually a 60-month loan at 0.5% per month. Unless you are told otherwise, always assume that car loans and mortgages have monthly payments. Okay, continuing with our car payment example. We're borrowing $60,000 for 5 years to purchase the car. The interest rate's 6%, so how much are your monthly payments? We can solve this using the TI-BAII 2+. Let's get it up here. First of all, we always want to do second, clear TVM to clear its little mind. Now we know we borrowed $60,000. I'm going to hit PV because the amount that you borrow is always the present value. Now I'm going to put in 60 for N because we have 60 monthly payments. That means that our interest rate also needs to be on a monthly basis. 6% APR divided by 12 months is 0.5% per month. So I'm going to say 0.5 I per Y. And I think we're ready to compute our payment. Let's give it a shot. Compute payment. I'm getting negative 1159.97. Why is it negative? Once again, this is the sign convention. That initial amount of money flowed to you to buy the car, and the payments flow the other direction, so they have a different sign. That's the TI-BAII 2+ sign convention. So this means that for $1159.97 a month for 5 years, you too can borrow $60,000 for a BMW, provided your credit allows you to get a good rate like 6%. Okay, let's try another example. Let's this time find the amount borrowed. Remember that the amount borrowed is always the present value. You have a car loan with 6.35% interest. Recall the car loans are quoted as APR, which means we need to divide this by 12 to get a monthly interest rate. Our payment is $526.39 per month. And we're going to be doing that for 5 years, but we're not going to enter 5 as our number of periods. We're going to do 60, which is 60 months, the same as 5 years. The question is, how much did you borrow? Now remember, the first thing you always want to do with the TI-BAII 2+ is second, clear TVM. That'll clear its little brain. 526.39 payment. 60 for N, that's the number of payments. 6.35 divided by 12. Now you have to hit equal here or this will not work. Then hit I per Y. Then we're going to compute the present value. I get minus $26,999.95. Now once again, notice that the negative is merely as a result of the sign convention of the TI-BAII 2+ calculator. Let's try an example where we find the interest rate. You've borrowed $300,000 over 30 years. Your payments are $3,085.84 per month. What is the APR on your loan? First of all, second, clear TVM. That monthly payment is 3085.84, and we hit the PMT button. Now we put in 360 for N. Why? We've got monthly payments over 30 years. 30 years times 12 months per year is 360 months. And then we have 300,000, that's our present value, but because of the sign convention, I'm going to put a negative in front of that and hit PV. Next, I'm going to compute I per Y, and I come out with something slightly more than 1%. But is this the APR? No, this is a monthly interest rate. To find the APR, we must multiply by 12. So our interest rate is 12.000000957, but in this class we round to 2 decimal places and we get 12.00%. Next we're going to work an example where we find the term or length of the loan. You've borrowed $100,000 at 10% interest. Your payments are $1,321.51 per month. What is the term of this loan in years? We'll say second, clear TVM, clear its little mind. 1,321.51 is the payment. Notice that's monthly payment, so we need a monthly interest rate. So we're going to take that 10 APR and divide by 12. Gotta hit the equals or it won't work. The I per Y button is next. Then we're going to put in the amount of the loan. That's the present value. But remember the sign convention says we have to have that be negative since our payment was positive. Now hit the PV button. I think we're ready to compute N. Now check this out. It looks like N is equal to 120. Does that mean that the loan is for 120 years? No, remember that our payments were in months and our interest rate was in months, so N is also in months. What is 120 divided by 12? 10 years, so that's how we get to that answer. Okay, so far we have been doing what are called ordinary annuities. These are annuities where the payment happens at the end of the period. But what if payments happen at the beginning of the period? Then we have something called an annuity due. Ceteris paribus, which is fancy Latin talk for all else equal, annuities due have a higher present value because you get the money one period sooner. Remember, we would all like to have money sooner rather than later. Now your TI-BAII 2 Plus can handle annuities due quite easily. Let's look. What you want to do is hit second and the payment button. Right now your calculator should say end. Now your calculator will give you some hints as to how to change things. For instance, right now it says set. If you look down here on your calculator, set is right above the enter key. Anything that's above the keys you have to use the second button to access. So we're going to hit second and enter, and notice it changed to BGN. That's meaning that the payment happens at the beginning of the period. Now if I hit clear, I want you to notice it says BGN right here. They give you that reminder because if you don't remember to switch this back, you will be in a world of hurt when you start doing ordinary annuities again. Your answers will be wrong. How do I switch it back? Second, payment, second, enter, and clear. Notice now that the BGN is gone. Now you're ready to work ordinary annuities again. Earlier we mentioned that annuities due have a higher present value than the same ordinary annuity. In other words, the same number of payments and same size of payments. So let's work an example to show exactly how much an annuity might be worth more as an annuity due than as an ordinary annuity. Here's the example. Your crazy aunt has given you the option of receiving $1,000 per year at the beginning of each year for 20 years, or receiving the same payments at the end of each year. Interest is 5%. Which one's worth more? How much more? So how are we going to do this? And we'll do second clear TBM as always. Let's do the annuity due first. Remember, to do that, we need to do second payment, second enter. And that puts us into BGN mode for annuities due. We're going to put in 1,000 for the payment, and we'll put in 5 I per Y. Now we don't have monthly payments here, so we didn't have to divide by 12. And we don't have to multiply the number of years by 12 because these are annual payments, so 20N. Now we'll compute the present value. I get minus $13,085.32. Now remember that minus is just because of the sign convention. So I want to keep this number in the memory of my calculator because I'll need to subtract from it later. First thing I want to do is hit the plus minus key. That gets rid of the negative. And then I'm going to do store 1. That's going to store it in memory location 1. We'll need it later. Okay, now let's take a look at the ordinary annuity. We're going to have to switch back. So we're going to say second payment, second enter. That puts us back into end mode, and I'm going to hit clear. Now, I don't recall if I hit second clear TVM or not, but if I didn't, all I have to do is hit compute present value because all the numbers are identically the same. I just needed to change the mode on the calculator. For the ordinary annuity, I'm getting a present value of $12,462.21. So let's find out what the difference between these two is. Let's see, I'm going to hit the plus minus here. I'll say store 2 on that one. Recall 1 minus recall 2 equals, I'm getting $623.11. Now you may have noticed that I named these things, I put them in 2 different memory locations. We can have up to 10 things stored in memory, 0 through 9. And this can be very handy later on in the semester. So, we knew the annuity due was worth more, we just did not know how much more, but this is how you find out. By the way, this is a popular question type for homeworks and exams. Sometimes we have to deal with uneven cash flows. This is especially true when we are considering a project like building a factory or buying a machine. These things seldom provide us with even cash flows like an annuity. And so we need to have a method for finding the present value of such cash flows. Here we have several uneven cash flows and our required return is 7%. It appears that we are going to invest $10,000 at time 0 to receive different cash flows in the future. How do I know that that $10,000 is an investment? It has a negative sign in front of it, so that is a cash flow out of our pocket, and the remaining cash flows are cash flows into our pocket. One way we could do this would be to find the present value of all of these individual things, either using the calculator or using our formula, present value equal future value divided by 1 plus r to the t, and then we could just add all those present values together. But that's a lot of work, and the calculator can do this for us much more easily. Okay, let's learn how to do uneven cash flows on the TI-BAII 2+. We have a required rate of return of 7%. These are the same cash flows as our last slide. And what we want to do is figure out what is the sum of the present value of all these things. Now once again, we could do each one of these individually, but that would take a lot of time and you'd probably make a mistake. Better to let the calculator do the work. So let's get our TI-BAII 2+. And the first thing we want to do is hit CF, second, clear work. This is important because your calculator will remember everything you ever did to it unless you clear it out. And if previously you had more cash flows than we have here, the calculator will continue to remember them. So the first thing we do is to put in the time zero cash flow. In this case, it's 10,000 negative, representing an investment. We're going to hit the enter key. If you don't hit enter, it's like it never even happened. And then we're going to arrow down. C01, the first cash flow after time zero, is $2,500. Once again, we must hit enter or it never happened. Arrow down, F01. This is the number of times that cash flow happens in a row. And here it happens twice, so we're going to say 2, enter. Now be careful, if this number down here were 2,500, we could not put 3 because there is a different cash flow in the meantime. Now we are going to arrow down and C02. You say, wait a minute, didn't we account for time 2 by telling it that we had 2 of these cash flows? We did. What this thing is actually asking for is a second unique cash flow after time 0, and that's going to be our time 3. So you hit 0, enter, arrow down. Now that cash flow only occurs once, so we're going to leave F02 as 1. Then I'm going to arrow down and enter 7500, enter. This is the third unique cash flow, 1, 2, 3. But it's actually at time 4, which calculator knows that. If I arrow down, we can see that F03 is already set to 1, which is correct because this 7,500 only occurs once. Now in order to find the sum of the present value of all of these things, we hit the NPV key. And the reason the NPV key works is because all NPV is the sum of the present values of all the cash flows, accounting for the fact that investment cash flows are negative. Now we've been told the required return is 7, and so 7, and we're going to enter, or it's like it never even happened, and we'll arrow down, and then the calculator tells you what to do right there. It says hit the compute button. So we do. And this asterisk lets you know that this number was computed by the calculator. And so the answer here is $241.76. If we found the present value for all of these individual cash flows and added them together, the answer would be $241.76. And if we were looking at this as an investment project, we would think it was a good one because the net present value is positive. In other words, this project at 7% will create almost $242 in new wealth. Now we'll talk about the different types of loans. The first is called a pure discount loan. That allows us to borrow a small amount of money now in exchange for paying one single larger lump sum of money later. The later payment represents both principal and interest. What are the examples of this in the real world? Well, we've got treasury bills. Treasury bills usually of about 3 months in duration. You might pay $900-something to receive $1,000 3 months from now. That's a pure discount loan to the federal government. Then we have commercial paper. Commercial paper are short-term discount loans to industrial companies. For instance, General Electric could borrow money using commercial paper, maturity of 270 days or less. You would pay them a smaller amount of money in hopes of receiving a larger amount of money within the 270-day period. That 270-day maturity is set by federal regulation. The next type that we see is an interest-only loan. That allows you to borrow an amount of money and pay only interest on that amount until the maturity of the loan. That's when we pay back the original amount and any remaining interest. The example here is bonds. Bonds pay interest payments called coupons throughout their lives, and at the maturity of the bond, you receive the last coupon payment plus the face value of the bond back. And finally, we have amortized loans. Amortized loans have payments that represent both principal and interest. This is the one that most consumers are familiar with. The examples here are mortgages and car loans. In amortized loans, the principal gets paid down over the life of the loan. However, that first payment has the most interest of any of your payments because at that point you owe the most money. But as you pay down the loan, your payments represent more and more principal and less interest. That very last payment on your mortgage represents very little in the way of interest. It's primarily principal. Now we're going to learn how to create an amortization table. In our example, we are going to borrow $5,000 for 5 years at 9% interest with annual payments. What an amortization table does, by the way, is show you how much of each payment goes toward interest and how much goes toward principal. But we don't have to worry about that quite yet because the first step is finding our annual payment. Well, fortunately, this is just an annuity and we can use our TI-BAII 2+. First thing we do, second, clear TVM. We've borrowed $5,000. That will be present value for 5 years, that is N, at 9% interest, so 9I per Y. Then we will compute the amount of the payment. Now notice the negative sign. Once again, that's just the sign convention of the TI-BAII 2+. We have $1,285.46. So now that we have that information, we can construct the table. We start with our beginning balance in year 1, which is $5,000. We have our first payment of $1,285.46. But we need to know how much of that goes to interest and how much to principal. We know we borrowed this money at 9%, so 0.09 times 5,000 is $450. And so of that first payment, $1,285.46, of that $450 went to interest, so the remainder, $835.46, must have gone to principal. How did we get this number? Simply take our payment, subtract the amount of interest paid. Then, to find our ending balance for the year, all we do is take our beginning balance and subtract the principal paid, and that gives us the ending balance for the year. That ending balance for the year will be the beginning balance for the next year, and it will be what we pay interest on in the second year. How much interest? Well, we multiply this number times 0.09, and we find that we are going to owe $374.81 in interest for the second year. And if we subtract that interest out from our annual payment, which stays the same, we see that this time we paid $910.65 in principal. And we can subtract that from our beginning balance to get our ending balance of $3,253.88. And that ending balance simply becomes the beginning balance for the next year. Now we can continue to do this exercise every year until finally we see that at the end, the beginning balance is precisely equal to the amount of principal that's paid throughout the year, giving us a zero ending balance, meaning that the loan has been paid off. Now don't let this bother you if this number here turns out to be 1, 2, or 3 cents. This number is likely not even cents, so there's probably some other money out here, so all of these numbers are going to be a little hairy. So don't let that freak you out. In fact, I can demonstrate that situation here. If you look at adding all the payments together, it comes out to $6,427.30. That represents the entire principal and interest paid on the loan. But if you add all the interest payments together, you see the interest payment is $1,427.31. If I add that to the principal that we paid, I get $6,427.31. So we have a 1 cent discrepancy between these two numbers, but that's simply as a result of rounding. One question finance professors love to ask on exams is to ask a student what is the total interest paid on an amortizing loan. And if the student isn't thinking clearly, they figure they must create an entire amortization table in order to learn this number. But if they remember that each payment represents both principal and interest, then they will remember all they need to do is take the payment amount, multiply by the number of payments. That gives you the total amount of principal and interest paid. And then all we have to do is subtract out the original amount borrowed, or the principal. What's left over is the interest. So this is a much simpler way to find out the amount of interest that you are going to pay on a home loan compared to creating an amortization table for 360 different payments. We can prove to ourselves that this works using the previous example. Let's take that payment of $1,285.46 and multiply it by 5. That gives us $6,427.30. And then if we subtract the $5,000 we originally borrowed, it leaves us with $1,427.30 in interest, exactly the same as we got from totaling up the interest paid on the amortization table on the last slide. Now we're going to ask one of the most important questions in all of finance, and that is, what is anything worth? Now we're talking about a financial value here, not emotional or sentimental or anything like that. Pure financial value. The price or value of anything is the present value of the future cash flows coming from that thing, discounted at a rate appropriate to the risk of those cash flows. So what's the relationship between risk and reward? As risk goes up, so must reward. I'll give you an example. If I offered you $60,000 a year to drive a truck between here, Springfield, Missouri, and Joplin, Missouri, you might be willing to take that. Now, if I offered you that same amount of money to drive a truck between Baghdad, Iraq, and Tikrit, Iraq, would you be willing to do it? Probably not. Why not? Well, it turns out that that route is much riskier, and as a result, the people that drive that route must be rewarded for that risk. The people who drive that route, in fact, are usually making six-figure salaries. Is it because they have high levels of education? Absolutely not. Most of them have at most a high school education. It has to be the risk that makes that job pay so much.